Welcome back, and now we are going to get into related rates fully and solve some exercises. So generally when we do related rates, the 6 steps here I have illustrated are very useful. Number one thing that trips students up is that they don't read the problem carefully. So that's why it is number one and in all caps. Make sure to read carefully. But after that, the second most critical thing is to draw a diagram and represent the problem that's in words as a picture. Because sometimes when you have the picture, it makes the problem go a lot more smoothly. Introduce notation, label quantities, find a relationship or an equation, and then number 5, this is where our calculus comes into play, is we need to recognize, yes, these quantities are changing with time, and we introduce a time derivative. And since our variables are likely not time itself, when we do that, we have to differentiate implicitly. Okay, and then only after we have found we've applied a derivative to our equation, a time derivative that is, then we can substitute in. So that's the other critical thing, is that students like to substitute in early. There are things where you can do this and be okay, but for our purposes, it'll be easiest just to say, do the substitution at the end. All right, first example. A cylindrical tank. Okay, I'm going to stop there. I read it. I'm going to draw a cylindrical tank. Okay, here's my cylindrical tank. Okay, radius 5 meters. Okay, here's a radius. And at our moment, we know that radius is 5. Okay, but that's at our moment. Okay, again, I'm not going to use that right now. Is being filled with water at a rate of 3 cubic meters. So there's some water coming in, and it's coming in at 3 cubic meters. Oh, cubic meters, not cubic centimeters. Cubic meters per minute. Okay, and we want to know how fast is the height of water increasing. Okay, so I drew a picture. Introduce notation and label quantities. Well, I've labeled the R, right? I don't know, let's see, so cylinder, there's going to be an H. I don't know what that is. And then this 3 meters. So I know in step 3 here, if I think about this, I'm going to say that the 3 here, 3 meters cubic per minute, that's a volume per time. And so I'm going to say that, oh, that's the change in volume with respect to time. And I also know that radius is 5. Okay. So I think that's all the information that was presented to me in the problem. And then I guess, what is it that the question is asking? How fast is the height of water increasing? Well, the height of water is h, right? But if we're looking at how fast the height is increasing, that's a rate at which height is increasing, right? So that's a rate, that's how fast it's changing. That's a time derivative. So we want to know effectively how many meters per minute is the water increasing. So that's my goal. All right. Now, for number 4, I have to determine a relationship that relates all the quantities in this problem. Well, I have a radius, I have a height, and I have a volume. Luckily, we remember that volume of a cylinder is pi r squared h. Okay. Now, for our purposes, every variable here we're going to think of it as potentially a function of t. So really, when we're writing this, we should write like v of t is equal to pi times the radius of t, and then we would square this whole thing, and I'm going to put that in parentheses, and then also height is changing according to time. Okay, we're looking at one specific moment in time, but the volume, I guess this would be the volume of water in the cylinder, is really what this equation would represent. Okay, so we acknowledge that these are all time-dependent quantities. All right, so now what we want to do in step 5 is we want to take our equation that we found in number 4 and differentiate both sides with respect to t. And when we do this, we have to do implicit differentiation. So, and let me maybe just do this in a different color here. Let's do this in blue. Okay, so then when I apply a time derivative to volume, I just get, it would be 1 times dv dt using implicit differentiation is equal to, and then there's going to be a pi. Oh, I have a product here, so I have to use a product rule. So I do 1 r of t squared times the derivative of h, so that would just be 1 times dh dt. Okay, and then plus 2h of t times, and then 2r of t times dr dt. Okay, using the power rule and remembering we have implicit differentiation. Okay, now for number 6, this is where I can substitute values in. So dv dt, I know that that is 3, and then I get pi radius at our specific moment in time. Well, actually radius is always 5. Okay, this is one example where you could have substituted the radius in and you would be okay. And then times 1 times dh dt, that's what I want to find. Okay, h of t is, oh, I don't know what h of t is. Okay, and then 2 times r is 5, dr dt. Okay, so now I need to think about this, dr dt. Is the radius ever changing as time increases? So is the radius always 5, or does it increase or decrease over time? The answer is it does not. So this rate is actually 0, okay, which is very fortunate for us because I did not know h of t, so that just allows me to eliminate that whole second term. And then when I solve for dh dt, you can check it on your own, but I got 3 over 25 pi is equal to dh dt. All right, so then this is a problem in context, so you should respond in context. So I'm going to say the height is increasing, the height of water, if you wanted to be specific, the height of water in the cylinder is increasing at a rate of 3 over 25 pi meters per minute. Okay, so this is the entire exercise. To recap, start by drawing a picture. Okay, that's step 2. We read carefully, that was step 1. Step 3 was to identify the quantities needed and the quantities that, or the quantities that are given, the quantities that are needed. Number 4, find an equation. Okay, recognize that the quantities are all time dependent, or they change with time potentially. Anything that doesn't change with time is effectively a constant, so we could have just said r is always 5 in this equation. Step 5 is to differentiate both sides of your equation. And then step 6 was to substitute, and in our substitution process we recognized that the radius did not change as time changed, which meant that the change was 0, and then we were able to solve.